Okay, last section we dealt with the interior angles and exterior angles of polygons, and now we're getting into actual properties of quadrilaterals. Now the first property, or the first polygon that we're talking about, the first specific quadrilateral, is a parallelogram. Now the parallelogram, if I go back to my first page, okay, remember yesterday we started right here, or the last time we met, we started right here. A basic quadrilateral, something with four sides. Okay, the first property we learned was that the interior angles add up to 360. Today we're moving into this shape. Okay, we're moving down our flowchart, and we are on parallelograms. Now, parallelograms have a lot of different characteristics, and what I'd like you to do as we go through them in our notes, I would like you to write them on this page. The reason for that is you don't have to flip through the different sections on a quiz or a test. You can just go to this very first page and say, oh, I'm dealing with a parallelogram, here are the characteristics. Or, oh, I'm dealing with a square, here are the characteristics. That's a trapezoid, these are the characteristics. It's easier to have everything on one page, condensed, than to have everything spread out. So, as we go through these notes, make sure that you're constantly flipping back, as you'll see me do, to be able to write down the different properties. Now, the first property that we're told is that a parallelogram is a quadrilateral with both pairs of opposite sides parallel. So, because both pairs of opposite sides are parallel, I'm going to draw the parallel symbols on the top and bottom and on the sides. I'd like you to make sure that you're doing this also. Looks something like that. Now, as I go back to my notes, the very next thing that I'm going to do, and I want you to do this also, is at the very top we're going to draw three different parallel line or four different parallel line structures. Okay, we're going to draw that one. We're going to draw that one. We're going to draw that one, and then that one. So you should have those four. And what I'm going to do is, and this should be at the top of your paper also, I'm going to specifically highlight that. And I'm hoping that parallel lines are starting to kind of flood back into your memory. And then on the second one, I am going to do this. And I hope that you're able to recognize that special pair of angles. Then I am going to do this. And we are going to identify those. And then last but not least, we are dealing with these. And I hope that all of these you are able to identify and able to tell me the properties of. For example, these two angles, they are called alternate interior angles. And do you remember what they have in common? Well, they are congruent. These are called consecutive interior angles. And do you remember what they had common? They are supplementary. These two angles form the F, which are called corresponding. And they, just like the alternate interior, are congruent. The last one we're going to do looks kind of like an is not equal symbol. These are called alternate exterior angles, kind of a goofy looking spelling, but alternate exterior, and they are also congruent. Those four types of angles are only brought about by parallel lines. Well, because you have parallelograms where the top and the bottom are parallel, I can promise you this: you will be constantly looking and solving using those 4 types of angles. Very important. The next property that we're told in Theorem 8.3 is that not only are the top and bottoms and the sides of parallelograms parallel, but they are also congruent, which means we need to go back to our parallelogram on the very first page. And we have the parallel symbols, but we also need to mark the congruency symbols. Then we're going to go back. So we've got parallel lines, we've got congruent segments, or congruent sides, and now Theorem 8.4 tells me that if a quadrilateral is a parallelogram, then its opposite angles are congruent. Well, I need to mark that, and I'm going to use this color. This angle and this angle are congruent. This angle and this angle are congruent. So I have 3 properties so far, not to mention all the different parallel line angles that I'm familiar with from previous chapters. And let's keep going. Here in example 1, we're told to find the value of x and y. Now, before we go on solving this, make sure that you have these written down. You can also write them in sentence form over here to the left. Okay. In fact, I'm going to very quickly. Okay. We're going to say opposite sides are parallel. We use the parallel symbols, so we don't have to write out the long word parallel. We're going to say opposite sides are congruent. We're going to use the congruent symbol, so we don't have to write out the word congruent. We are going to say that opposite angles are congruent. Okay? So those are the 3 properties that we have for a parallelogram. We're going to go back to our notes and start solving these. If we look at x, if we look at where x is, first of all, x is an angle. And if I think of parallelograms and what I know about angles of a parallelogram, I know that opposite angles are congruent. Well, I can see that I am given the opposite angle, so if they are congruent, then they are also equal. And if they are equal, we set them equal. 2x equals 50. And now I'm going to use my algebra and divide by 2. And I get x equals 25. So there's my x, and now I'm going to solve for my y. Now, if I can identify y, it is right here, meaning it is a segment or a side. If I remember the properties of a parallelogram, sides, opposite sides, are also congruent, which means that if this side is y plus 3 and this side is 18, those 2 sides are congruent, which means they are also equal. And if they are equal, we set them equal. And I have a simple algebra problem to solve. I'll subtract 3, and I get y equals 15. Beautiful, beautiful, beautiful. Again, like I told you in the previous section, the math behind these problems is very, very easy. There is not a lot of complexity to these algebra problems. We just divided by 2 and subtracted 3 to solve 2 problems. Come on, that's easy. Now, example 2 asks us to solve for FG, which is right here, and to find the measure of angle G, which is right here. Now, I want you to look at that problem. And I'm going to tell you, I'm going to give you a little hint. There is no math involved in this. No math whatsoever. Can you find the measure of FG? I hope you're saying to yourself, the measure of FG is 8. But I'm going to ask you why. Why is FG 8? And I hope you're saying to yourself, FG is 8 because its opposite side, HE, is 8. And in a parallelogram, which you can see parallel, 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 this is a parallelogram. In a parallelogram, opposite sides are congruent. And congruent means equal. So if one side is 8, the other is 8. What about angle G? How much is angle G? I hope you're saying to yourself that it is 60 degrees. And the reason it is 60 degrees is because its opposite angle, angle E, is 60 degrees. And in a parallelogram, opposite angles are congruent. So if angle E is 60, then angle G is congruent to angle E, meaning angle G is 60. Real complicated math there, folks. Please try to keep up. Let's go to the next page. And Theorem 8.5 says, if a quadrilateral is a parallelogram, listen to this, then its consecutive interior angles, I'm actually going to highlight those. Consecutive interior angles are supplementary. Supplementary meaning they add up to 180. Now, I want you to stop, and I want you to flip back to the very first page. Excuse me, the very second page. Okay, let's try the first page of section 8.2. There we go. Hope you're keeping up. Sorry about that. And I want you to look at the different parallel angles, or the angles formed by parallel lines that we got. Notice this blue one. Mine is blue. Yours probably isn't blue unless you're using markers. Consecutive interior angles. We mentioned that they equal 180. Hello. We already talked about this. This should not be something new. Congratulations. They're telling me that it's equal to 180 or that they're supplementary, but I already knew that. If this line, let me use a different color. I'm sick of this Joker looking green. That's better. If these two lines are parallel and they are cut by a transversal, oh look, they form consecutive interior angles. And I remember when we had the chapter on parallel lines, consecutive interior angles are supplementary. So I already knew this. They didn't need to tell me that. But I want you to look at the very next theorem. Theorem 8.6 says that if a quadrilateral is a parallelogram, then its diagonals bisect each other. This is a new characteristic. We need to go back to the very first page, and I promise it is the correct page. The very first page of our notes, and what I'm going to do is I'm going to draw two line segments going across, or two diagonals, excuse me, inside this parallelogram. There they are. Yours don't have to be perfect. Mine are perfect, but that's just me. Now what I'm going to do is I'm going to show that they are bisected. And if they are bisected, then these two are congruent, and these two are congruent. Okay? Make sure that you're following that. Make sure you understand that the diagonals of a parallelogram bisect each other. I'm going to write that right over here also under my list of properties. Wow. Let me try that all over again. That was some sloppy handwriting. Diagonals bisect each other. There. So now I have four properties. Aside from opposite sides being parallel and congruent, opposite angles being congruent, now I have diagonals bisect each other in a parallelogram. I'm going to go back to my notes and flip the next page where I've got some problems to solve. This is a guided practice showing you different properties of a parallelogram. Now in this problem, or in these problems, you're going to be solving for line segments or sides, and you're going to be solving for angles. What I would like you to do is take the properties that we know, okay, those four properties we just talked about, and I would like you to go through and solve these 8 problems. Solve for NM, KM, and then the next 6 angles, or 5 angles, excuse me. Go ahead and do that now. Pause the video. All right, hopefully you were able to solve for NM, KM, JML, KML, and then the other 3 that we'll go over in a second. But I want to go over these 4 first. This is a parallelogram, as denoted by this statement. That symbol is a parallelogram, and then they label it JKLM. Because they tell me right away it's a parallelogram, I already know 4 properties. I know that diagonals bisect each other. I know that opposite angles are congruent. I know that opposite sides are congruent. and I know that opposite sides are parallel. So what I'm going to do is I'm going to use what I know and what they give me in this image to solve for these pieces. Now the first thing they tell me is NM. NM is highlighted right here in yellow, and NM is part of the diagonal KM. Well, because it's a diagonal, I know that it has been bisected, which means that this segment is congruent to this segment. And if KN is 2, then NM also has to be 2. Therefore, NM equals 2. The very next problem tells me to solve for KM, which, if KN is 2 and NM is 2, and KM is made up of KN plus NM, KM is just 4. Most of you were like, wow, really all that for just 4? Yes, it's that important. Don't blink. You'll miss something. Then we go to number 3. And JML is highlighted in red. Now, what I'm going to do is I'm going to write down a property that we need to use. And the property of this parallelogram that we're going to use here is that opposite sides are parallel, meaning this side is parallel to this side. And because those two parallel lines, watch this, parallel, parallel, cut by a transversal, what does that mean that these two angles, wait for it, these two angles have to add up to? I'm hoping you're saying to yourself they equal 180. So what I can do to solve this is take this part, which I can call x, and this part, which is 110. If this angle is 110, and I know that this part is made up of x and 30, I can say x plus 30. And all of it should equal 180. You can see here that the 110 isn't a part of it like 30 is. 110 is the entire angle on this side. Whereas this side, this little piece is 30 and this piece is x, which means this whole angle here is x plus 30. That's just the angle addition postulate, by the way. So now I'm going to solve this for x. And I'm going to combine my like terms and get x plus 140 equals 180. I'm going to subtract 140 from both sides and get x equals 40 degrees. Well, now that just solved for x. That didn't actually tell me JML. And let me erase all this so you can see where JML is. JML is right here. Well, I can see that JML is made up of these two angles. This one's 30, and I just solved this one to be 40. So that means that JML is 30 plus 40, or 70 degrees. Now, notice the next problem. The next problem asks for angle KML. Didn't we just solve for that? The answer is yes, we did, and it's 40 degrees. Now let's go to the next problems. It says find the indicated measure in parallelogram EFGH. So what I'm going to do is just go through and highlight these so we can solve them. Angle GEF is right here. And GEF is part of two parallel lines. And let me show you something. We have a parallel line and a parallel line cut by a transversal. Now those form alternate interior angles, and I hope you can see that. Alternate interior angles are the Z. Alternate interior angles, notice this, alternate interior angles are congruent. So when I go back to my problem, I know that this angle and this angle are congruent. Whoops. If this angle is 45, that means that this angle is also 45, which means if this is the angle I was originally looking for, GEF, I just found it using my alternate interior angle theorem. It has to be 45 degrees. Hopefully that makes sense. We used alternate interior angles, knowing they were congruent. We identified that GEF was congruent to EHG, or EGH, excuse me, so that if one is 45, the other has to be 45. Remember, you can always pause this video, go a little bit slower, stop it, rewind it, do whatever you need. Next thing we're going to do is look for EHF, which is right here. Now this one's a little bit different. It does not pull in some of the properties of a parallelogram, but you'll notice that when we drew the diagonals, we broke this parallelogram down into 4 what? And the correct answer is triangles. And because we know a lot of properties about triangles, we spent a lot of time this year studying triangles, we know that the inside of a triangle adds up to 180. You'll see where that comes into play here in a second. Now, I highlighted these two diagonals intersection points for this very specific reason. If this angle is 60, what does this angle have to be? And I hope you're saying to yourself that it too is 60, but now I'm going to ask you why. Why is, let me re-highlight it, why is this angle also 60 degrees? And I hope you're saying because of vertical lines, or vertical angles, excuse me. Vertical angles are formed by two intersecting lines, and they are across from each other, so to speak. They are congruent, so if this side is 60, then this side is 60. Well, then you can see why I brought up the concept of triangles adding up to 180. Because we know that this angle is 85, this angle is 60, and we are actually looking for EHF anyway. So down here I'm going to write EHF plus, and then the other two angles, has to add up to 180. See where I got this? The triangle EHJ is made up of EHF, angle 60, and angle 85. So I'm adding all three together and it should equal 180. Now when I combine my like terms, I get EHF equals 145, or plus 145, excuse me, equals 180. If I subtract 145 from both sides, I get EHF to equal 35 degrees. Hope that makes sense how we found that, how we used vertical angles to find two of the three angles inside of a triangle. And once you have two of the three angles, now you can start using your triangle sum theorem. By the way, later in the chapter when we get into different quadrilaterals where the diagonals are actually perpendicular, think about this. If the diagonals are perpendicular, then they form 90-degree angles. And if they form 90-degree angles, the four triangles that are now created are right triangles, which pulls back in all the stuff from last chapter. Pythagorean theorem, sine, cosine, tangent, inverse sine, inverse cosine, inverse tangent. All those properties come flooding back. And they're not hard. They should be a review at this point. But yes, we've already gone over them. Now, the last thing that we're told to solve for in this guided practice is angle HFG, which is right here. HFG. And this is what I want you to see. Here's HFG, and it's highlighted. Now, I'm going to pull back a concept or a property that we rewrote up here. We used it in the previous problems to solve, but it's the theory, or it's the idea that opposite sides are parallel. Let's say that we take this side and this side, which are parallel, and we cut them by a transversal. Whoops, what kind of angles were formed? Alternate interior angles. Now I'm going to write something down. We already used vertical angles to solve for this angle as 60. And we used our triangle sum theorem to say the interior of this triangle right here makes this angle 35 degrees. I want you to notice this. This angle and this angle are alternate interior angles, which means they are what? Congruent. If EHF is 35, then HFG has to also be 35 because they are congruent. Now, you could have used the interior angle theorem to find out what a triangle adds up to be. You could have used different alternate interior angles. Either way, you have to use parallel lines to solve for some of these problems, which means that if you skated through a couple chapters ago when we went through parallel lines and didn't really learn them, you could be in trouble here. It's just a big review. We're applying what we already know. This is a great representation of what you're doing on your homework tonight. In fact, let's take a look right now at what you're doing. Okay, today we're going to start Chapter 8. And Chapter 8, at the beginning of your notes, you'll notice this quadrilateral flowchart. Now, this quadrilateral flowchart is kind of the thing that's going to guide us through Chapter 8. And I'll give you an example. We start right here with just a regular quadrilateral, something with 4 sides. And then the next section we move down the flowchart, and when I say move down, I mean we take this regular quadrilateral, something that has no special characteristics. It just has 4 sides, 4 random sides, none of them being the same length, no angles that are special, nothing like that. And we move into something called a parallelogram. And when we move down the flowchart, we add properties, meaning this quadrilateral has a lot of properties to it that we're going to find. And then you'll notice from this parallelogram, we can actually move left to what's called a rectangle, or we can move right to something called a rhombus. And then you'll notice the flowchart actually gets smaller again to something called a square. At the very top, you'll also notice that instead of going to a parallelogram, you could go to left to a trapezoid, and trapezoids have different properties than parallelograms. Or, starting with a regular quadrilateral, you could move to something called a kite. And a kite has different properties than a parallelogram and a trapezoid. So what you'll see is as we move down, we're going to use this first page as kind of a guide to write down new properties next to each new quadrilateral. And the reason we want to do this is you're eventually going to be asked what quadrilateral has these properties, and you're going to have to say, oh, it's a rectangle. Or you might be told this shape is a trapezoid. And the moment somebody tells you that it's a trapezoid, you need to be able to look and see, oh, because it's a trapezoid, it has all these principles. The top and the bottom are parallel. The consecutive interior angles are supplementary. The diagonals are congruent, stuff like that. And we're going to find out what all those characteristics and properties are. But today what we're going to deal with is just a basic quadrilateral. Now go to the first page, or the next page, and we start in section 1 dealing with the angle measures inside polygons. And before we can get to the angle measures, there's something that we need to go over called diagonals. And a diagonal is simply a line segment that connects 2 vertices. A vertice is a special word for an angle. If you take any angle, or any 2 angles, and you connect them with a line segment. Let's say you take B and E, and you draw a line segment there. That is called a diagonal. Let's say that you take D and A, and you go from A to D, or D to A. That is also a diagonal. And again, a diagonal is just a segment that joins 2 angles. We're also going to talk about the interior angles of quadrilaterals, or generally polygons. Now, let's talk about the word polygons. Poly means many. Gon is just a word for a geometric segment. So this is many segments, meaning many sides. Now, specifically, we can name special polygons. You all know what a triangle is. Tri has the prefix of 3, and then angles, well, that tells you that it has 3 angles, really not that hard. What we can do, though, is based on the number of sides, or any number of sides a polygon has, we can figure out what the sum of the measures of the interior angles are. Meaning, what does the total interior angles, or what do the total interior angles add up to be? Now, this isn't that hard. You've already been exposed to something like this when you deal with a triangle. The inside of a triangle adds up to how much? Most of you are already saying it in your head, it's 180 degrees. You already knew that. You already knew that if you take the 3 sides of a triangle and flatten it out, you get 180 degrees, you get a straight line. But what we're going to find out is the more sides that you add, like let's say you go from a triangle to a quadrilateral, okay, 4 sides, we find out that it has more than 180. In fact, we can take any quadrilateral, break it up into 2 triangles, which means that the interior angles have just now doubled. But what we're given in geometry is a formula that tells us if you take any number of sides of a polygon, let's say it's 6, you could plug 6 into this equation, n minus 2 times 180, and you can find out what the interior of any polygon is, whether it has 3 sides, 4 sides, 5 sides, 100 sides. You can plug in the number of sides into this formula and find out what the interior of the shape or the polygon adds up to be. And we're going to find out why that's important in the next page. But aside from that, you're also told this: the sum of the measures of the interior angles of a quadrilateral is 360. You already knew that. We knew that any quadrilateral, whether it's a square or a rectangle or a trapezoid, you can, in any one of these, you can randomly cut it into 2 triangles. And because it's 2 triangles, it has 2 180-degree measures, which means 360 degrees. This corollary is just telling you, if you know something has 4 sides, don't bother using this formula. You can just always guarantee it has 360, just like a triangle. We don't plug in 3 when we want to know how many angles or what the total of a triangle adds up to be. We just already know that it's 180. From now on, know that a quadrilateral has 360 degrees. So this formula to find the interior angles of a quadrilateral, we're going to use that on the next page to go through the different types of polygons you're going to be exposed to. So go ahead and turn the page. Here we see in example 1, we're told to find the sum of the measure of the interior angles of a convex, and then we have pentagon, hexagon, octagon, nonagon. Now, you're going to need to know different prefixes, meaning words that are used to describe a specific number. You already know, bi, okay? Bi is a prefix to determine 2, whether it's bicycle, okay? Bicameral, something that has 2 cams, like a bow or a car engine. Then we have the prefix tri. And tri, you already know, with tricycle and triangle is 3. Then we have quad, and some of you already know this because you have ridden quads. A quad has 4 wheels. A quadrilateral has 4 sides. Then we go to penta. And some of you are already familiar with penta because of the Pentagon in Washington, D.C. The Pentagon has 5 sides. Then we have hexa, which is 6. We have hepta with a P, which is 7. We have octa. Whoops, I don't know why I made that a Q. Octa, which is 8. Nona, which is 9. Deca, which is 10. Really, these are the only ones that I require you to know, and bi really doesn't matter because you really never have a biagon. You can't make a geometric shape with 2 sides. It's physically impossible. It has to have at least 3. The only other one that I'm going to require you to know on a quiz or a test, but I will also remind you of it, is something called a dodecagon. And this has 12 sides. The rest of these, from 3 to 10, I do require you to memorize, especially for quizzes and tests. And you'll see why. As an example 1, you need to know them. Let's say you were looking for the interior angles of a pentagon. Now, a pentagon, you should already know, being we just talked about it, has 5 sides. What I'm immediately going to do is plug 5 into my formula, n minus 2 times 180. And so I have the problem. Make sure you're writing this down, too. Don't just take it for granted like, oh, I can figure that out. Because it does get harder as we move along. Once you have this down, it's simple math. In fact, you can plug this entire sentence on your calculator. We get 5 minus 2, which is 3, times 180, which is 540 degrees. So the interior of a pentagon, something with 5 sides, adds up to 540. A hexagon, again, we just went over it, it has 6 sides. So again, I use the formula n minus 2 times 180. I plug in my 6. And what I find is when I take 6 minus 2 times 180, I get 720 degrees. What I'd like you to do now is solve for the interior measures of an octagon and a nonagon. Pause the video and do that now. Okay, hopefully those problems weren't too tough. An octagon, something with 8 sides. We take 8 and plug it into the formula n minus 2 times 180. And what we get is 1,080 degrees. Remember, this is what the interior of an octagon adds up to be. If I quickly draw an octagon for you, the interior of an octagon adds up to 1,080 degrees. Then we do the same thing with a nonagon, something with 9 sides. Excuse me. We take 9 minus 2 times 180 and we get 1260. Now there's a little note here, and I want you to think about this before you just answer. If the polygon is regular, regular meaning all of the sides and all of the angles are congruent, could you find the measure of each interior angle? You know what they all add up to be, but could you find the measure of each interior angle? And the question is, or and the answer is yes. If we redraw our octagon, we redraw our octagon very quickly, we know that all of them add up to 180. Okay, we just figured that out here in letter C. Well, there are 8 angles. And because it's regular, all of those angles are congruent, which means that I can actually do this. I can shove the same variable into all of them. And when I add them all up, they should equal 1,080. So what I get is the problem 8x equals 1080. Not 10 comma 80, but 1,080. Well, when I solve this and I divide by 8, I find each interior angle to be 200. And let me finish punching it in my calculator. To be 135 degrees. You can take the interior angles, as long as the shape is regular, meaning all the angles are the same. You can take all the angles, the sum, and divide it by the number of sides, and you find the measure of each interior angle. Hopefully that makes sense. Let's look at example 2. Example 2 tells me that the sum of the measure of the interior angles of a regular convex polygon is 900. I want you to think about this, because this is telling me the answer to my problem is 900. Then it says classify the polygon by the number of sides and find the measure of each angle. This problem is asking for, what is this shape called? Well, you can't tell what it's called until you figure out how many sides it has. That's what we're looking for. We can take the formula n minus 2 times 180, which gives me the interior angle sum. Well, they just told me the interior angle sum is 900, which means it equals 900. Whoops, don't do that. So I can take this problem and solve for n, the number of sides. So if you look at this problem, and using our algebra skills, the first thing we need to get rid of is this 180. We need to get rid of it because we want the n minus 2 by itself. So I'm going to divide both sides by 180. And what I get is n minus 2 equals 5. Now I'm not done yet. I can't say what I have as a pentagon because I still need to solve for n here. The way I solve for n is by adding 2 to both sides. What I get when I do that is n equals 7. Now the question is, classify the polygon by the number of sides. What's something with 7 sides called? And all you have to do is look at the very top of our notes to figure out that it is a heptagon. And then it says find the measure of each angle. Now this is something we just discussed in the note. If the total interior angles add up to 900 degrees, and there are 7 equal angles, I can write the problem like this. 7 times each interior angle equals 900. If I divide both sides by 7, I find out that each interior angle equals 900 divided by 7, and I get each to be 128.57 degrees. Now, I hope that makes sense, and I hope that's not too complicated. Let's look at this page once again, because you have to, this is a good reflection of what you're going to be doing tonight on your homework. You're going to have some problems where you're told to find the sum of the measure of the interior angles. You're going to have some problems where they give you the sum and ask for the number of sides, and maybe even ask you to name it. And then some that ask you for each individual angle, which is what we did here. Go ahead and turn to the next page and you're going to see a guided practice problem. Pause video. Erase previous statement. Go to the next page and you'll see two more problems. In Theorem 8.2, the exterior angle theorem, if you take any shape, or any polygon, excuse me, okay, here we have a quadrilateral, and what this theorem says is if you extend the sides to form straight lines, then we tie in an idea that you've already been dealing with all year long. You bring in the idea that exterior angles form straight lines, and a straight line equals 180 degrees. Which means, if you think about each of these angles, like this, we'll call this one x for now. X plus this exterior angle form a straight line. Well, if a straight line is 180, then you can say this angle plus 1 equals 180 degrees. What this tells you is the sum of the measures of the exterior angles of a convex polygon. Convex polygon meaning any number of sides. Something that has 10 sides or something that has 4 sides. All 4 of these exterior angles are going to add up and equal 360 degrees. If I draw a quick, let's call it a hexagon, something with 6 sides. If I draw a quick hexagon, and I take all of these lines, or all of these sides, and I draw straight lines out of them. Call that 1, 2, 3, 4, 5, and last but not least 6. All of these exterior angles have to add up to 360 degrees. It doesn't matter if the shape has 6 sides. It doesn't matter if it has 4 sides. The exterior angles always add up to 360 degrees. Not too confusing. It's just something that you need to get used to. A simple statement, just like a supplementary angles always add up to 180. Exterior angles of any convex polygon equals 360. Let's take that and apply it in example 3. It says find the exterior measure of each angle, meaning we have to find each individual angle, of this convex polygon. Well, like we just got done discussing, it does not matter how many number of sides this shape has. The exterior angles have to equal how much? The correct answer is 360. Well, now what we can say is this angle plus this angle plus this angle plus this angle plus this angle equals 360. So I can say 4x plus 4x plus 4x plus 4x plus 4x equals 180. There are 5 of them. Well, when you add 5 4x's, you get 20x equals 360. Divide both sides by 20. You get x equals 18. So I know that x equals 18, but that doesn't tell me each angle measure because each angle is 4x. So I take my 4x, substitute my 18 in, and what I find is that each individual angle is 72 degrees. Let's back up and let's remember that we took all of the exterior angles and said they have to equal 360. All 5 exterior angles add up to 360. Well, then we solve for x, plug that into our angle because we want to know what each individual angle is, and we find out it's 72. Now, if you think about it, or I'm telling you this is where your homework assignments are going to go, because you know the exterior angle is 72 degrees, could you figure out the interior angle? Now I'm going to ask you, why can you figure out the interior angle if you are only given the exterior angle? What do the exterior and the interior add up to be? The answer is 180 degrees. If the exterior angle is 72, then the interior angle is 180 minus 72, or in this case, 108. Well, if you were to figure out that this interior angle is 108, well, maybe you could use that to solve for the other ones. Go to the next page. And now we see 4 guided practice problems dealing with 4 different shapes and solving for different pieces. You'll notice in number 1, you have to solve for an interior angle. Number 3, they're asking you to solve for an exterior angle. Number 4 and number 2 are similar to number 1 in that you have to solve for an interior angle. Remember the difference. What does an interior angle add up to be? What does an exterior angle add up to be? Are either of them dependent on the number of sides of the shape? What I'd like you to do is pause the video, review your notes, and I would like you to go through and solve these 4 problems now, and then when you're ready, hit play and we'll go over the correct answers together. Okay, just like last chapter with sine, cosine, and tangent, these problems can take a while, but they are by no means hard. They are very simple algebraically and geometrically. And you'll see that as we go through them. Now, if you got them wrong, not a big deal. We make simple mistakes sometimes when we're solving big problems. All you have to do is just look at the algebra and see where you made a simple algebraic mistake. It could be something as simple as just writing down the number wrong. But you'll see that this first problem, I started off by saying it has 4 sides, which means the interior adds up to 360. And then I actually wrote a statement where all 4 angles equal 360. When I do that, I get 277 plus x equals 360. Subtract 277, you get x equals 83 degrees. The second problem, I started off by saying it has 5 sides, which means the interior angle theorem interior angle theorem determines that it equals 540. And we do that by saying n minus 2 times 180. Plug in 5. We get 3 times 180, which gives me 540. Then you can see that we started off writing our sentence. 5x plus 139 plus 9x plus 71 plus 92 should add up to 540. We combine our like terms to get 14x plus 302 equals 540. We subtract 302, then divide by 14, and we get x equals 17. You go down to number 3. Now number 3 is different than the other ones because it deals with exterior angles. So I started over here by saying exterior angles equal 360. Then I come over here and I write all my exterior angles, add them up and make it equal 360. Combine my like terms to get 150 equals 7x, or plus 7x equals 360. We subtract 150, then divide by 7 and we get x equals 30. Now the fourth problem is a little bit longer, but we can just look at the thought process, the steps to solve it. We start off by saying it has 7 sides. When I use the same interior angle theorem that I used in number 2, I find out that a 7-sided object, the interior angles add up to 900. Then I actually went through in this step and actually wrote down all the angles, added them together, make it equal 900. Now, because of the lack of space, I solved this one on a different piece of paper. You combine your like terms. Your like terms are 102, 124, 146, 158, and you end up adding all those to equal 530. Then you add up your 24x, your 34x, and your 16x, and you get 74. Well, when you subtract 530 from 900, you get 370, and you end up getting 74x equals 370, divide by 74, and you get x equals 5. Now, the geometry statements, okay? If we look at these, let me highlight them so you can see. That's a geometry statement. That's a geometry statement. That's a geometry statement. That's a geometry statement. If you understand where we got those and how to find those on your own, you're well on your way to making this chapter one of the easiest chapters that you'll see this year. Aside from chapter 9, the rest of the chapters are very simple. meaning 8, 10, and 11 are very simple. This chapter, it doesn't get much different than this right here. Very simple geometric statements that if you can set up yourself, know where we got it, know how to find it yourself, and solve it accurately, you're going to blow this chapter away. Okay? But let's go ahead and take a look at what we learned and apply it for your homework tonight.